itself, that will not give me identity. All right. So if I were to keep going and building up this basis until I have n-dimensional bases, then effectively QK is going to be QK hat transpose inverse. Okay. Now, so the question is, how are we going to generate these bases? Because before we had some sort of recurrence relation, or we used Gram-Schmidt. So we want to use the same kind of idea to generate both of these bases. And then see how we can use them to solve AX equals B. So let's focus on basis generation now. And what you'll see is it's a fairly direct generalization what is done for generating one orthogonal normal basis. So we're going to prescribe that these vectors are equal to polynomials of A times B. So we have these polynomials of P0, P1, etc. generate the Q's, and then we have a different set of polynomials, P hats, also polynomials of A times B, to generate the Q hats. Okay, so same formula that we've had. Okay, now a Gram-Schmidt-like recurrence relation. So we use the same framework for generating new vectors from previous ones. So for the Q's, for instance, I'll have beta j qj plus 1 is equal to a qj so I'm assuming that each vector is expressed in terms of previous vectors in this manner. So I'm throwing A into the mix to build my Krylov subspace. And I have to subtract off the appropriate multiples of the previous Q's in order to make sure I have the whatever property I want. Now before, like on Monday, I wanted orthogonality. Now I want biorthogonality. So I'm going to take the dot product of both sides of this equation, not with a Q, but a Q hat. So, okay, so what I'll do is I'll multiply, let's see, I'm going to take a dot product of both sides with QK hat. And by linearity, I have Q, K hat, transpose Q, I. All right. Now, I'm going to assume that K is some integer between 1 and J. So this dot product is going to be 0. So 0 on the left side, and then, okay, then I have Q hat transpose A, Q, J over here, and then, due to biorthogonality, all of these terms are going to go away, except when I is equal to K, in which case it's 1. So the only thing that's going to be left is HKJ. So I have this relationship, and actually just by rearranging it, I now have these coefficients in my linear combination are just going to be these dot products. Now, but the thing is, now suppose I represent these vectors in terms of, from a Q has, this is a Credo subspace using A transpose, so I need A transpose here. Okay. All right. So now what I'm going to do is I'm going to replace both of these, this Q hat and this Q, by these polynomial forms. So I'm going to have, from here I have B transpose, P hat J minus 1. Now here I have a transpose, but I'm taking the transpose. So that's going to leave me with just A in this case. And then I have this A, and then I have P, this is a K. And then I have J minus 1 of A. So notice in my dot product, all I have is functions of A. There's no transpose here. And this is equal to HKJ. All right. Now, I can think of this as a sort of inner product, in a way. That so this is an inner product of lambda times P K minus 1 of lambda with P J minus 1 of lambda. Now, I have to make sure that this QJ is orthogonal to all QJ hats, except when the index is the same. So what that means is this polynomial of degree J minus 1 has to be orthogonal to all polynomials of lesser degree. So what that means is this dot product here is equal to 0 whenever so this dot product is equal to 0 if K is less than J minus 1, because and the reason for that is I'll make sure I don't mistake my notes here. Okay. Yep. I do have a mistake in the notes, which I will correct here.